As you can see, the detailed output, you can print this one. You can also perform the shear design, the links, the stirrups. You can do this. Now, our interest here is to perform the column sizing. So let us discuss this one. So for the column sizing, first of all, I'll turn the AutoCAD on. Let me close this one for ETABS. Let's concentrate. I'll just concentrate with prota first, because for the ETABS, we will have to do some other things. Now, for this one, what is the procedure for performing the column sizing? The first thing to do is for us to know the size of the slab. That's the first thing, to know the size of the slabs. So how do we know the size of the slab? We have two ways. The first way is through engineering experience. I think I discussed that one with you while performing while putting the beam dimensions. The engineering experience. So for this one, that's why as an engineer, you have to have someone who can guide you as an engineer. Like for me, I have my senior actually guiding me. Here we go like this, we do this, then you'll be a professional engineer, or you'll be a consulting engineer at a faster rate. So you must have someone to guide you. I think that's well noted. So through that, because for this building, through pre-design, you can end up getting a slab of, for example, 175. But that is totally uneconomical for someone outside here. So an engineer will just tell you, please use 150 millimeters. Now, is 150 going to serve? That's now a question for you as a designer. So I don't know. We are going to do the pre-design for this building very fast. Though time is running, we've already used 1 hour and 4 minutes, seconds. I mean, minutes. So for this building, we are going to do the pre-design very fast. How do we do that? The first thing, let me just have this text, and please, kama haujatendi class yangu before, use this one as an opportunity to understand how slab pre-design is done. So the first thing, we always use deflection criteria. And what is deflection criteria trying to tell us? Here we have to get the span, the shortest span of each panel, the shortest span of each panel. So we are going to select the shortest span of each panel. For this panel, panel A, for example, we have 3,000 and 4,600. So we have LOI and LX. LOI is the longer side and LX is the shorter side. So you have to get the LX of each panel. And how to do that? You just do it by looking, by observing. So for this one is this 4,600 and this one is 3,000. So I'll just change this one to 3,000 because this one is the shorter side. Then I will copy this and populate it to these ones like this. And of course, I'll just do away with this. I'll populate to all panels so that we can do this one very fast. Now, let's continue. For this second panel, we are comparing 34 and 3. You'll find out that 3 is the smaller side. 35 and 3 is the smaller side, that's okay. For this panel, we are comparing, but now we have to monitor where we have the staircase. So for this one, sorry, we can just close this one. Good. So for this one, the staircase is at the third panel from top. So we'll just do this, then we'll come here. So this one here is where we have the staircase. So we have two types of staircase. Let's discuss staircase a bit before we continue. We have a staircase which are monolithically constructed with the structure. What does that one mean? This one means as construction is being done, at the same time you are doing the construction of the staircase at the same time. But we have staircases which are non-monolithic. This means you will construct them later. So what does this one mean? You can also perform the design of the design. You can perform the design and everything of the structure and do the design of the staircase later, because if the contractor is not going to do the construction of the staircase at the stage where the building is being constructed, why do you perform you can perform analysis and design later. I think that one is noted. You have monolithic and non-monolithic. Monolithic, this is done. You have to perform this design together as you perform the design of the other elements. Non-monolithic, you can just leave the staircase and do it later because it will be needed later for construction. So for this one, we'll assume non-monolithic. So I'll just do this, an X, to show that if you see an X to any structural drawing, it will mean either it's an empty space, or it's an open to sky space, or it's a place where we have a ramp, or we have a staircase, something like that. So you have to monitor that, or it's a space left for the lifts, something like that. Avoid. So for this one, we'll just leave this one for the staircase. Now let's come to this point. We have 46 compared to 2000. So this one 2000 will win. This one is 2000. I'll just type 2 because of time, 2. Then here we'll just use 2 like that. That is 2000. Then for this one, we are comparing 25 by 35. So this one is 25 because we are trying to compare 25 by 35 and 25 by 30. So 25 is the shorter span. For this panel, we have to understand what is this. So 1000 plus 25, that is 3500. We are comparing 3500 to 4600. So this one will be 3500. I'll just change this one to 3500. Then for this panel, we are comparing 25 to 35. So you'll find out that this one is 2500 because 25 is smaller. This 25 is LX because the LX is smaller side, the shorter side. Then for this panel, we are comparing, this one is 35. This one, 1000 plus this one, that is 3500. Then we are comparing it to 3500. So either way, we don't have the shorter or the longer. Shorter is equal to longer. So this one is 3500. Now, 35, sorry. 3500, something like this. So after highlighting all the shorter sides of each panel, so this is now the point. You have to select the biggest value or the longest length among all these highlighted white values. Which one is now the biggest? You have to select the biggest. So this one is 3, this one is 2, this one is 25, this one is 35, and this one is 25. So you'll find out that 35 is leading. But the problem is we have two 35s. Have this one and this one. So which 35 to select? Let me first of all delete these ones because they are not helping us right now. So among all these short spans, we have 235 as the longest spans. Now, as the longest spans. Now, which one is now? Which one are we going to use? We have this one. This panel is giving us 3500 by 3500, and this one is giving us 35 by 46. I know, without even telling, you'll just realize, apart from looking at the shorter span, now we'll look at the longer span. So for this one, we will use this one, this panel. We'll use this panel because this one is bigger than the 35. So we'll use this panel. We'll also delete this one. So at the end of the day, the span is 3500. So this span will have to go to table 3.9 of BS 8110 and perform the deflection calculation. Then from deflection, you can now get the height of the slab. How do you do that in Excel? Because I don't want to do that. I can see time is running. Now in Excel, we have two ways, as I said. You can perform, you will read this, that for this point, we have to select the height, select the H calculate if you like the workbook to perform the initial sizing the initial proportioning for you. Initial proportioning is like initial sizing of the slab. Otherwise, the other side, enter the value as per your experience and the nature of the structure. So we have three factors. One, do you have experience? The answer is no. Then what am I supposed to do now that I don't have the experience? You have to allow the Excel to calculate, or you have to calculate that. Otherwise, you have to use another person's experience, and of course, you have to look at the nature of the structure. What is this structure going to carry? That's another important thing. Now, according to experience, you just have to select H experience. According to experience, then you will enter this value, but we are not going to use that. We are going to allow Excel to calculate the value of H, this value for us. Now, this value of H, it will request us to enter, it will request us to enter here it will request us to enter the span. This is the longest short span from all the short spans in the whole structure. And I think from this structure, we had some short spans to each panel. But now, which one was the longest? We had the two longest spans. From these two longest span, we now settle to this. And what is this? That 500 millimeters. So we'll just have to enter here at 500 millimeters, then Excel will give you the size like that. Like that. So 100 and at 500, then from at this point, you have to select the location of the type of panel that controls deflection for your building. That is the panel with the longest short span. So for our slab, for our model, which panel is that? This is the panel. Now, at this point, where is this panel? This is a continuous. We have three types of slabs. I don't know. I don't want to go to BS 110 today because of time. Do I have this code, by the way? Okay, I have it somewhere here. So, according to BS 110, we have three types of slab. We have continuous slab, we have simple supported, then we have a cantilever slab. So, for the continuous slab, you have to understand what is a continuous slab, what is a simple supported slab, and I think the video is somewhere there in Telegram. So, okay, table 3.9. A good practice is to master this code. Now, according to conditions, you have cantilever, simple supported, and continuous. So I don't want to explain this one, please, but just know the simple supported slab is the slab supported at all the edges. It's just one slab supported at all the edges. Then for the cantilever slab, it's just a one slab panel supported at the end, at the two. I think I have it. Let me just show you. Where is this? Okay. Now, for the cantilever slab, I think we know it's simple supported. Now, for the continuous slab, like for the slab that we are having, this one is a continuous slab because after this slab, we have another slab. There is some continuity. But for the simple supported slab, it is just this slab, this one. Then this slab is supported at each corner. We have the columns, and we can also put the water tanks at the top here. Now, that is a simple supported slab. What about for the case of the cantilever slab? For the case of the cantilever slab, we can just have this slab, of course. Then this is there. It's the what? This is now the beam. Let me turn this one off. Assuming that this is now the beam, then for this beam, we have a column here, we have a column here. Then this one is now a cantilever slab supported on one side only. Because the slab has four edges, we have this one, this one, this one, this one. So supported on one edge, that is a cantilever slab. But a continuous slab is the one supported. It's a slab that is having a near another adjacent slab. That's now a continuous slab. So for this slab is obtained. It's a continuous slab, but obtained at the end of the building because we have this. This one is the interior slab. This one is interior, but this one is obtained at the end of the outside the building. So how do we put that one in according to Excel? So you'll come here. Then we have some types of slabs here. We have a continuous slab, but at the end, continuous at the interior. So ours falls at this point, continuous end slab. Then continuous interior, assuming that, for example, we obtained our deflection span at this point, then we will have to select continuous slab, but interior span, continuous interior. So for this one, we'll just select continuous end. And then we have other slabs like cantilever slab, simple supported, and so on. So we'll just select continuous end slab. After selecting this, of course, now look at this. This is now where we get these factors. We have this modification factor of 1.3. We'll discuss this one where we get this one. Then the basic ratio. This basic ratio is actually obtained from table 3.9 of BSA 6399 here. For the continuous rectangular slab, the factor is 26, yeah. So this 26 is here. Then we also have to look at cover. How do we get cover? The cover for the slab, just be using 25. I will tell you how and why. 25 is obtained from table 3.3 and table 3.4. Actually, be writing these things down because we are not going to rely on BS today because I think it's within me. BS is within me, so we'll just use it. So to get the cover for the slab and the beams, you'll go to clause table 3.3 and table 3.4. Table 3.3 will give you the cover based on the environmental conditions, that is severe or mild or whatever. Just go to that BS, then you'll read more about that. Then table 3.4, it will give you the cover to the structure based on the fire conditions. Fire conditions, like the point is, how long is this structure going to resist fire before the fire brigades arrives with their machine with water? You just have to figure out. So it gives the cover based on the hours that these guys will come and save the building when it catches fire. So you just have to select according to the two tables. Now, which table is giving you the bigger value, the biggest value. So for that one, you just find out we have 20 and 25, and we always use 25. So for this one, I can just assure you be using 25 for slabs. Then because in field we always use for the slabs, we always use the thickness of the slab. We always, I mean, the bar size, we always use 10 millimeter dia. Then we always assume this one. So for this one, we just assume 10 millimeters. And for after setting all this, our height is calculated as 150 millimeters. Please take note of this. 150 millimeters is the height of the slab. Now, take this 150 and come with it to this, to column sizing. To column sizing, we have to say to know the number of columns that our structure is going to have. For example, do I have this? What is the name of this? Not what? Notepad. Not okay. Or paint. Let me use paint. This one. Now, using this paint, I'm going to assume this. I'm going to assume this is our structure, something like this. I think you can still see my screen. So if this one is our structure, then assuming that this is the ground level, then we have the first column here. This is the first floor. Then we have the second floor. Then this is the third floor here. Then we said we are going to assume a fourth floor structure. Sorry, something like this. This is the fourth floor. And then this is now the roof slab. So on top of this roof slab, we can put some water tanks. We just discussed this one, but I'm not going to put the water tanks today, but we'll discuss them as we progress. So this is the ground level. This is the ground. Then this is the first floor, second floor, third, then fourth. Then this extension, this is now the parapet walls, or the parapet walls. I think we all know them. The extension of the walls to put some barriers at the roof slab. So this is now the parapet. Now, how many columns is our structure having? We have one column here, we have the second one, then we have the third, then we have the fourth. We don't always use the parapet as the part of the column. We always mention the main columns here. So the main columns, we have 4 columns. So for these ones, but for this building, I just want us to use 5 columns. So 5 columns, this will mean we have G plus 4. G plus 4. So we'll put another column here. This one. So we have 5 columns. Then this one will be the parapet. The parapet. So I'll just put 5 here like that. So that is it. So we have a column running from ground level to first floor, then first to second, second to third, third to fourth, then fourth to the sub. As you can see, from this one, we have this column from ground floor to first floor to second, second to third, third to fourth, then from fourth to fifth. As you can see, from fourth now to fifth is now our roof slab where we have our water tanks. I think that point is well understood. Please, if you have any query, just raise your question to the chat box, then we'll discuss. Then the slab thickness, all of them is 150. You can just type 150. For example, if you have 175, you can just type 175. Then you drag like that. Then all your slab thickness will be placed. The second thing is now to enter the SIDL. What is SIDL? For the loads, we always have some loads to our slab. We have now. I'll just go to slab after initial proportioning. We'll go to proportioning. For the final proportioning, self weight will be calculated because the density of concrete we have selected 24. auto-calculate. We have the partition loads. How do we enter the partition? How do we know the loads of the partition loads? The minimum value, as you can see, this value has to be based on the number of walls that we just left aside as partitions. For example, I'll show you the example here. Now, for example, we just left this wall aside, this one. We don't have this wall. Why? This wall is now used as the partition wall. We just left this one aside. So, the minimum partition load, now from your engineering experience and knowledge, you have to figure out now which figure am I going to use, because that one is based on assumptions. There's no figure that is now, it will tell you that this is the partition load. You just have to assume a certain value. But the good thing, the code will give you the limit, the lower and the upper limit. The lower limit, you'll go to BS6399. You'll go here to BS6399 part 1, clause 4. Part 1, clause 4. Let me open with, I don't like using this thing. Okay, let me open with the edge. Nice. Okay, opening with the edge will help me. Now to clause 4. Here, clause 4. This clause 4 will tell us something important. We'll discuss this one. Please take note of this one, because there's something important we are going to discuss from here. But now, partition loads. Where do we get partition loads? Clause 5.14. 5.14. Because of time, as I said, I'm not going to read all through, but be quoting down these ones, then they will help you. But when you read, it will now tell you that the minimum here, the partition load, this additional uniformly displayed partition load should not be less than 1 kilonewton per meter squared. What does it one mean? The partition load, whether we have partitions or not, you have to at least take 1 kilonewton. You don't 0. You just have to take a minimum value. What is the minimum value? 1 kilonewton per meter squared. Now, what about the maximum value? The maximum value, okay, time is of essence. We have codes to tell us all this, but now write this one down. We will discuss. I will tell you the code. The minimum value is 1 kilonewton per meter squared, and the maximum 2.5 kilonewtons per meter squared. Because you are not going to leave all these walls aside as partitions, you'll have to consider some walls, just some as partition loads, and those are some of the loads that you'll now consider. So the minimum is 1 kilonewton per meter squared, and the maximum is 2.5 kilonewtons per meter squared. Please take note of that. So in a range of 1 to 2.5, which figure as an engineer think is allowable for your building? And as you can see here, these beams, I mean these partition walls, these are the walls which are not adding anything to they are just walls placed on top of the slab. Please take note of that. And the range is 1.5. So in that range, what do you think is the load for this building? As you can see, there is actually no loads, unless otherwise, if we inside this bedroom, the client to come up with a small partition to include his bathroom inside this, then we can now treat that one as a partition load. Otherwise, for that building, there's no much partition load, so we can just use 1 kilonewton per meter squared. Now, for the surfaces and finishes, surfaces for our buildings, we have the tables, we have tables, we have beds, and so on. So all those things that are giving you service, those are some of the loads that you are supposed to consider them as permanent, the dead loads. So for the surfaces, we always take 1 kilonewton per meter squared. Then for the finishes, some of the finishes, we always recall tiles, we have the ceilings, we have some cabins, the shells, all those things, I think we will know them. So for the surfaces and finishes, we always consider 1. So the sum is 2 kilonewtons per meter squared. But the thing that you should be changing is this one, the partitions. You just have to play around and see the partition for your building and use in a range of 1 to 2.1 and 2 to 2.5 kilonewtons. What do you think is the right thing? So you have to put. Most of the people always use 1.5. For this building, we could have used 1.5, but as you can see, actually, we don't have partitions. So it's only this small wall, which is 2 meters. That is, we cannot consider it as a major partition wall. So for this one, we just use 1. Now, the sum of the partitions and the surfaces and finishes, this sum is what we call SIDL. If we go to ETABS, is when you'll understand this. So this one is what we call extra dead load to our floors. Otherwise, we can also call them super embossed dead load. These are a dead load which are on top of the slab, which are on our slab. The tiles, you know them. The partitions, they are just there. We know them. So these are a superimposed dead load. So this superimposed dead load, as you can see, is the summation of partitions and surfaces and finishes. So the sum is 3 kilonewtons. So I'll just enter here 3 kilonewtons, please. Okay. Okay, just a minute, please. You can see there is something that has to be. Just a minute. Just a minute. I'm just here doing something. I know for most of us, we are using our phones to have the internet. So try to make sure you be online, because this you can't afford to. You don't have to miss this session, please, unless otherwise. I understand for most of us, you receive the calls and so on. So immediately after the call, make sure you come back to the meeting. I think I'm done. I can now share my screen. Good. Okay. Now, I think you can now see my screen. Yes, I think you can now see my screen, guys. So here, we have to enter the dead load as we saw from the slab tab here. The total of this extra dead load is 3 kilonewtons per meter squared. So this 3 kilonewtons per meter squared, you have to type it here. Then after that, you have to just drag and it will populate at this point. Another thing, this top slab, this top slab, as you can see, we have several slabs. We have 1, 2, 3, 4, 5. But now look at this drawing. For the slabs, we have this one as the first one. We have the second one, the third, the fourth, then the fifth. We have 5 slabs. This top slab is now this one. This is now the top slab. For this top slab, this super embossed dead load, if we come back to this tab, we don't have partitions. We don't have the surfaces and finishes. We have so many values. So as an engineer, remember, engineering is all about trying to figure out, trying to come up with assumption and make sure you use those assumptions to design your building. So now that we don't have the partition, of course, the dead load for this building, we can the partition load for the top slab 1, we have to reduce 0. So for this one, we'll just reduce it to 0, of course, to 2. So here we'll just put 2 kilonewtons per meter squared. Then another thing here, because we are using, this is the roof slab, we have to get the load for the roof slab. This load has to be obtained from BS 6399 part 3. That is for the roof loads. So part 3, let me just go there. Part 3 is here. So this part 3, I dislike this thing. I will have to uninstall it. Okay. Now, remember we have roofs and roofs without access. So please, I'll request you that you read the minimum embossed roof loads. So we have minimum embossed load on roof with access. Roof with access, these are the roofs where people can access to do some cleanings, or where people can actually settle. For this one is a roof with access because we can put some water tanks here, or people can just come and relax on top of this roof. So roof with access, as you can see, please read all through. But now the point is the uniformly distributed load is 1.5. Then for the roofs without access, the minimum embossed load is 0.6. That's why when you come to this Excel, at this point, we have 1.5, 0.6, and 0.75. Where is this 0.75 coming from? I'll just show you, but please go and read. 0.45 is here. It's a special case. When you read, you'll find it here. So here that providing the above conditions are met, and allows should be made for an embossed load equal to or greater than that which produces the worst load effect from one of the following. So one of the following, this one, the improvement, you can use 0.75. So it depends with you. Please read and get more information about that. But for our building, it's a roof with access. So for this one, you'll just use 1. We'll just use 1.5. Then what about for this? This is a residential building. Where do you get the loads for the residential building? That one, you'll go to table 1 of BS 6391 part 1. I think that table is on this one, this BS. So table 1 is somewhere up here, this one. So this table has 4 columns. The first column will give you the category of the building. The second one will give you the examples of that building. Then the third will give you the loads to that building in kilonewtons. That is the uniformly distributed load. That is the pressure loads, of course. Okay. Okay. Now, this table 1 will give you the live loads. And we have several columns, as I said. We have the first column, the type of the building. The second one will give you the loads, the example of the buildings. Then the third one will give you the loads in pressure way. Then this one will give you the point loads. But always be using the uniformly distributed load. Now, our building is a residential, is a building for residential activities. So for residential activities, as you can see, this one is domestic and residential activities. So our building is under this row, the first row, or the category A. So for category A, you have to be very careful in looking at these examples and select the load. So for this one, you have all usages within self-contained or a single family dwelling or communal areas, including kitchens in blocks of flats. This one is bedroom and dormitories, except those in single. Then this one will give you the bedrooms in hotels and motels, and so on. So our building, you'll just realize, sorry, it is falling at this point. So at this cell, the load is 1.5. So this is the load that we should actually be using. But remember, this one is the minimum embossed floor load, minimum. So as an engineer, you can actually opt to increase this one to 2 kilonewtons or to the saw load. So for this one, just use 2. I don't want to use the 1.5. It's so small, or let's use it because we are actually using the code. But according to experience, please, you can use 2. So 1.5. After that, as you these cells, these ones are the formulas. The next thing is to enter the story heights. So for the story height for this building, we just use 3. Then the beam will use 450 by 200. This is what we discussed. Then for the be calculated. Then the walls, because we want the beams and the walls to flush, the thickness to flush, we'll just use 200, this one. Then we'll have to come up with some assumption. We have to assume some columns. So we'll assume 200 by 200 column, and that is. Then are we dealing with a rectangular or a circular column? Of course, for this building, we just use the rectangular column. Now we will start. We have 3 types of columns. We have corner columns. We have this corner, these are the corner columns. Then we have the internal columns, and we have also the perimeter columns. Perimeter column is the one supporting 3 beams. This one, and this one. Corner column is the one supporting 2 beams. Then internal column is the one supporting 4 beams. This one, and this one. So we have to start sizing of the sizing of our of the columns. So we'll start by this. How do we size this column? For this column, we just have to get this span and this span 3046, and when you put this one, then the Excel will give you the size of the column. So first of all, you have to select the type of column. It's actually the corner column. As I said, you have corner, perimeter, and internal. So you'll select the corner column. As you can see, it will request you for 2 dimensions. The first dimension will be dimension A. Dimension A, as we saw from this one, is 3000 and B is 4600. So here 3000, then here is 4600. So after that, are we going to reduce the, now this is a very nice point. Let's go back to this plan. Now, as you can see, to this plan, from this plan, we have a window here, then we have another window here. So what does this one tell you as an engineer? Of course, we are going to assume, the assumption is this wall, we are going to have an entire wall to this beam. But in reality, that is not the case. So as an engineer, you have to reduce, or you have to remove this wall, because this is our window, this is our window. So how do we reduce that one? It's also an assumption. So we have to reduce that one using the percentage. So we can just reduce this one. It's just an assumption. You just have to know the size of this window from the architectural details and the size of this one, then you do some assumption. So for this one, we can just assume 20% reduction, like that. I'll assume that one. Then after doing this assumption, the density of the wall, we will use 18 kilonewton. We have several values, but we'll just use 18. Then we are using BS81 with BS81 10, so the factors is 1.5 and 1.6. This one for today, because we are not going to print, but we can print this after that. Now, the assumed value, if we assume 200 by 200 for this structure, then the other side will be 128. As you can see, for this building, we can just use 200 by 200 column, because the figure is small. So 200 and 200 will work. So here I'll just enter 200. Sorry, 200. 200. What if I use 200 by 100? You'll realize this one is telling you have to the column section is. So the right, use 200 as a square column of 200 by 200. So for this one, let me just close this one, because now turn on the column layer, this one. Then I'll just draw the column. So I'll just draw 200, type 200, and then type 200, like that. Then take this column, move, and it, my snaps are off, take it to the center here. That's the first one. So as you can see, this one is 3000 by 4600, and this one is 3000 by 3500. If this one is giving you 200 by 200 column, and this one is, of course, this is going to give you even a smaller column. So what we are going to do, instead of designing that column or precising that column, we'll just use this one and populate this column to the other figures by looking. So this one is 3500 by 3500. We can try this. You can try 35 by 46 and see, because this one is 3500. What you will do, you just come here and change this one to 3500 and see if the size will increase. As you can see, it's 200 by 141. So 200 is still working, because there's no warning here. So for this one, you'll just come here. You can just copy this one, copy. Then I'll just paste this one at this point, like this. So all the corner columns set. After corner, we will come to the perimeter column. So for the perimeter column, you just come to this Excel, switch to perimeter. It will request for A, B, and C. So A is the beams following each other, then C is the beam inside. So if we take this one, A is 46, B is 34. A is 46. This one is 4600. B is at 400. I'm trying to be faster. Then C is the internal beam, and this internal beam is 3000. So this one is 3000. So for this beam, it is now requesting 200 by 199. use 200 by 250. Now this is now a small experience. For this column, we can use 200 by 250. So we'll just create 200 by 250 column, 200 by 250 column. But now another question is, how are we going to put this column? Because assuming that this is 200 by 250 column, we can either put this column to face this side, the longer side to come in, or to allow this column to go this way. But now, which is the best practice? The best practice is to get the difference between these beams. To get the difference between this beam and this beam, if we get this one to be 1200, if you do a simple maths, will give you 1200. And the difference between this beam and the beam above, as you can see, we don't have any beam above. So that 3000 my is 3000. So we are comparing 3000 and 1200. You'll realize this side is bigger than the difference of this side. So this column has to come to the side that is longer than the other side. So I think that is enough for you to understand. So this one will be 200. Then this other side will be 250 because this one is longer than ender, like that. And then I'll just copy this one and put it here. Now, I created two files, the one for prota and the other one for ETABS purposely. I will tell you the reason later. Then I don't want to perform the precising of all the columns, but in field you have to try and see. So this one is a corner column. So for the corner column, I'll just copy this and populate it here and here. Then we have the perimeter column. So perimeter columns, we have 250. So what I'll do, I'll just rotate this one by 90 degrees, turn on ortho, rotate, copy. Select, then rotate. Rotate this one. Sorry, rotate. Yes, this one is okay. This one is 250. So I'll just copy this one. Then what I'll do, I'll now take it. I'll take this one here. Then here. All these columns are at 250. Now, this what I'm doing is right, because the good practice, we know very well that this column has to flush with the beam. But if we do it right now, then it will give us a lot of work in prota. So I'm trying to avoid that. You will just see what I'm trying to do in prota structure. We can also put this one here because it's just a perimeter column. And we will push this column inside to flush with this beam. Then we also push this one inside to flush with that beam. What about for the internal beams? So for the internal columns, we will just, let's use, we can use, I want to select, we can use this one. You can use this one. Yeah, let's use this one. So for this internal beam, the dimensions we have 34 and 35. The beams following each other is 34 and 35. So first of all, you'll come here, then select, I'll come here and then select internal, like that. So CD is 34, 3400 and 3500, like that. Then what about AB? AB is the vertical ones. So for the vertical ones, 34 and 35. For the vertical ones, we can use this. This one is 35 and 25. This one is 3500. The sum of this is 35 and this one is 25. So I'll just use 35, 3500 and 2500, like that. So this one will give you 300 by 311. So we don't have this column. So the nearest column size we can use is 300 by 200 by 350 millimeters. Then that will be okay. Yes, engineer.
I think A and B is the one which is 35 and 25.
35, then 25. Sorry. Then CD. Oh yeah, CD. What about CD? Now CD is now 34, 35, right? Thank you for that.
Yes.
34. Then this one is 3500. Good. So after that, as you can see now, this one is 200 by 275. So 200 by 275, let me see. CD 3525. CD 3525. Wait. CD is this one. I think CD is 34 and 35. 34 and 35. Okay. That's okay. Then AB, the vertical ones, AB 25 and 35. Okay, this is noted. 25, 35. Okay, after doing this, so you'll get 275, 200 by 275. So we can actually use 300. Just what thank you for that, because any error will lead to oversizing of your columns. So for this one, we'll just to use 200 by 300. So I'll just type this column here, 200, then tab 300. As you can see, this is the longer side. So you have to figure out the difference between this beam and this beam is 1000. What about the difference between this beam and this beam? This one is 1200. So you'll realize your column has to go in a horizontal way. So what I'll do, I'll just copy this, put it here. Then I'll rotate. Okay, wait, I'll rotate. I have a point to make. Sorry. Rotate. My author is off. This is okay. So I'll copy this and put it here like that. Then I'll just turn on. Now, what I'm doing for those who we are interacting for the first time, we are doing what we call column orientation. Column orientation is important to eliminate or to reduce the column moments, because mostly we don't always want the column moments. The moment you introduce moments to your column, then moments, because if we talk of moments, this is just reinforcements. The moment you introduce moments, that is how you introduce reinforcement to your column. So we are trying to avoid moments. That means we are trying to reduce reinforcement to our structure. Please allow me to put these columns like this. As much as you understood the meaning of column orientation, I don't want to discuss that one. Let's discuss this one only, or let's take this, for example, this one. Let's see. This column. So for this column, you'll have to take the difference between this column and this one. The difference is 100 millimeters. Then the difference between this one and this one is 500. So actually, we have to put our column to face upwards, because 500 is bigger than the difference between these two. So for the sake of this, I'll just delete this and put this here. Then for this one is 1200. Then this one is 500. So this one is just okay. I think we can stop there. For column sizing, I think that's okay. Now, after doing the column sizing, we are done. God is good. You have to appreciate. We are done with everything. The next thing is now to import this one to prota structure. But before doing that, I want now to copy these columns to our model, to our ETABS model. And now, because we want to import all this to these softwares at the same time. So what I'll do, I'll just copy to copy these ones to ETABS. You copy one, you select one, then you right click, you select similar like that. As you can see, we have selected all the columns. Then what I'll do, I will copy using the specified point. So to copy using this point, what you'll do, you come here, clipboard, and then copy with base here. Then I'll pick this one as my base, the bottom part, this grid one. Then I'll come here. This is the grid one. Then I'll just paste this one. Then you put it there. As you can see, now we have all the columns. Now, what's the difference between ETABS? Why am I creating two things at the same time? ETABS is good. In ETABS, we don't need these beams. So I right click, select similar, delete. Before that, Control Z. This is the point. As you can see, this column is aligned, is perfectly aligned. But when we come to this one, when we come to this column, this one, as you can see, this one, we have to push it down. So in ETABS, this is something good. We'll just select this one, push it down like that. So I'll push this one also like that. Then because we have this, then we have this, I'll push them just together. Don't move up to that point. I think that's better. Then as we discussed, we have to move this one towards this direction. Now, for those who don't know how to install prota-structure, I just want to show you, because I don't have prota-structure in this computer. It will be a good thing for you to know, because most of them have been complaining. You're trying to install, but it's not working. It's not not okay. Do we have okay? So I think this is the last one. Now, please pay attention to what we are going to do, because now this is now what you call coming up with the layout. So in ETABS, you can actually delete this, or we can just leave them. Let's leave them. Okay, let's delete. We can delete or we can leave them. It depends on how we are going to monitor them, but let's just delete them. I'll select similar, then I'll delete. So the only thing that we have is the columns and the grid lines. So these grid lines are the ones that we are going to use to create the beams. But now pay attention to this. I have selected this one beam. This one beam, as you can see, it's just a continuous beam from to Z, which is a very wrong practice. The good practice will be this beam will come from this column to this column, from this column to this column, from this column to this column. Then after that, now ETABS will now do them perfectly. Now, how do we break these beams to come up with the splits? Because we have to split, we have to come up with the splits of this beam. How do we do that? I don't know. I think I don't remember how to do that, but I have a tool to do that. So I will share these two tools. You come here to manage, then load the application, then you have break all. So break all, you select this break all, then load the application, always load and then close. Then after that, now you have to select break all. You have to type break all. This one, break all. It is here, this. So it will ask you to select the object. So I'll select these beams like that. I'll select this, so that but there's no need of selecting that, but I'll just select them just to ensure that everything is done right. Then click enter. So as you can see right now, we have the bits. Otherwise, to break them manually, it will be so difficult. So we have these bits. So with this, we are good to go in it. Please note that. So what about in prota structure? In prota structure, with this, we are good to go. Now, let's start with the ETABS because I have it. In Excel, that is all. This Excel can do everything, of course. For this small building, you can just use Excel. Josephat, the one who just corrected me, we've been together doing a lot of things with him, so he understands this Excel well because we have been using it together, including developing the Excel. We have been developing the Excel with Josephat. Now, I want to open ETABS because that's the next thing. Now, in ETABS, I'll give you the procedure. Then, please follow the following procedure to do this thing in ETABS perfectly. And if you don't know how to install ETABS, reach me to my inbox. I'll create an online session with you, and then I'll advise. Now, I don't have a general guide to ETABS, but I remember someone, okay. Okay. In how to install prota-structure. I don't know if I have it here. If I don't have, I'll just switch to another computer and we'll use another laptop, or I think I have it here. It will take like 3 minutes. Don't worry with the time, because as it installs, we'll start with the ETABS. So let me come here. Softwares, prota, good, it's here. I'll copy. Then here, softwares, structures, paste. Now, the first thing to do is to turn off your Defender, because if your Defender is on, then it will take the crack files. So you just have to turn off your Windows Defender or any other antivirus that you have. Make sure you turn them off, and it will be nice for you to. Now, after that, I'll extract this software. So I'll just come here. This one is Windows 11, but it's just the same thing. Sorry. So this is a mistake. Good. So you just come to this one, then extract to prota this one. So as you can see, it's just taking some few seconds. Now we are okay to go. We are good to go. Double click inside and then go to install. Run. Right click, run as admin. Yes. It also depends with the speed of the machine. It depends with the speed of the machine. Now, okay. So we'll use the English version next. I'll just allow the laptop to install all this because these things are very important in coding. Then as it installs, let me copy the cracked files. You come into the patched. Then we have two files: Control A, Control C. Control A to select all. Control C to copy, like that. I'll minimize ETABS. As you can see, it's almost. So please give me 1 minute. I take water. Okay, I'm back. This one is almost. It will take like 30 seconds from now, and then we'll be good to go. Now, ETABS. At this point, okay, while installing this software, please don't put the company name, don't put your name, because the moment you put your company name, they will know, they will actually, there's some coding that will send the information to them that actually a certain firm or someone is using this software, and it will also take the serial number to them, so they will actually trace and know exactly where that computer is and how it is using that software. If you are designing some serious buildings like 20 plus floors, then it will detect and they will come for you to pay for the software. So don't put anything here. It's a request. If you put it at your risk, at your own risk, and the risk is now to pay some amount. So as you can see, Prota, it's now installing Prota Steel. This one is for steel design, and detailing. After installing Prota Steel, it will now install Prota Details, the one that we are going to use for detailing of our of our of the mold that we are just creating. You are going to see everything here. It's just a matter of some 1 hour here because the model would do some explanation. Okay. I want to explain about Prota first because Prota will take like 30 minutes, then we will be through. But you remember ETABS, hey, at the start of our meeting, this one is an extended three-dimensional analysis of building systems, not just building systems. So this means it's a very comprehensive software that we really want to cover in 30 minutes. Of course, we are going to cover everything in just 30 or 45 minutes. Then trust me, you'll be an expert in using these two softwares. But now the question is, why these two softwares? One of the client will request you that I want you to use ETAB. Another one will request you to use ProtaStructure. But now, if you don't have the knowledge of the two software, then it will be difficult for you to contemplate